Hello, and welcome to the 18th lecture in the Jabrah Reinforcement Learning series. And today we're going to be talking about approximate solution methods, or more specifically, the on policy prediction with approximation. So, before actually starting on that specific topic, I would like to give more of a motivation behind why we actually use these methods to begin with and what value do they give us when we're solving for reinforcement learning problems. So first, we've been through a couple of reinforcement learning algorithms already, but these were in very simple settings where the state space was manageable and the action space was either constrained or once again manageable. So this time we're going to look at how to deal with situations when the state space is too large, because we need some kind of representation as to how to deal with those large state spaces, because there are actually two problems that come with that, which is like we need a lot of memory if we're going to manage like these large tables, and we need a lot of data to fill them in accurately. And I'll give an example for what this means. So let's actually think about how we've been solving these problems lately. So far, let's say I'm gonna give a simple example here. Okay. So far we had a situation like this. So let's say each of these boxes is representing some particular state. And the question is, we want to find the value of each state in this representation. So what we would do, whether we're gonna be using Monte Carlo or like TD methods, the idea here was that to find the value of, say, this particular state, which I will denote as S here. So we want to find the value of S, right? So what we would typically do is we would generate an episode, right? So we'll generate an episode that's I'm just writing it in a more general fashion here. We say S1, A1, R1, and so on until we reach some final time step ST, as you know, and this is like, episode 1. And once again, we'll generate another episode, maybe starting from a different state, but here I'm just writing it in very simple terms and say this is our episode 2, and we would use all these episodes to update the states. So we can think of this as our table that we need to update, because we can say, for instance, if we're using a Monte Carlo based method, we'll say, well, the V at time step 0 of our given state S, right? Maybe we need episode 1 to actually find the true value of V at time step 0. At time step 1, we need to use values maybe from a different episode starting from that state. Here I'm of course ignoring like what type of Monte Carlo we're doing, whether it's first visit, every visit. You don't have to think about this right now. So, and then at VK, maybe we use like some episode K. Here I'm just very simplifying these things. So we needed to collect all these different episodes to update the value of the state until we converged eventually to its true value, VKS. So here I just gave an example with Monte Carlo, but if you think about all the other algorithms we've been looking at, the situation is the same. Like we need to generate all these episodes to fill in these values. So given that, we can consider this, right? All these episodes we need to generate, we can consider this our data, right? These episodes that, okay, let me undo that. So we can consider this to be our data that we need, or I should represent it here. This is our data. And like we need this data for all these different states. We need to generate all these different episodes to fill in all this table, to know the true value of this state, to know the true value of this state, to know all the true values of these different states. This is what we need to do so far. Now herein lies the problem. So imagine now this became our state space. Okay. Now our state space is a bit more difficult to manage, right? So let's say we want to try to find the value of this state. The problem has become a little bit more complex because now we need more episodes and in turn more data in order to actually find the true value of the state. So as you can imagine, the more we actually try to, the more our state space actually expands, the more data we need to actually represent each state. And if our state space is not manageable at all to actually fit into memory or something like that, we need a different way to actually represent it. So the problem here is that when we're actually training, if we don't have sufficient data anymore, there are some states that won't actually have their true values because that means to actually get the true values of every state, we need to generate way more data. So a limited amount of data means that we won't be able to represent as much. So we want to find a representation where we learn with as little data as possible. And if you think about it, it's not only the state. If we introduce actions into this mix, right? So the moment that we introduce actions, now we're trying to estimate the value of, say, qs comma a, right? This actually, for each and every state, in this case, maybe there are 4 actions, but what about when there are 10 actions or 12 actions or whatever? Like, how do we actually manage this situation? So since right now, as usual, when we encounter a new reinforcement learning algorithm, we start by solving the prediction problem and then the control problem. We're not going to bother solve with the action space as much, but we're going to focus on the prediction problem. So this actually brings us to a topic, which is on policy prediction with approximation. So there are 3 keywords to identify here. On policy, which means, as you remember, that the target and the behavior policy are the same. The prediction problem means that we are given some policy pi and we're just trying to find the value of each state under that policy. And approximation means that we are no longer representing our state space by using this kind of table that we showed here, but we're going to start using like function approximators. We're going to be representing everything with a parameterized function. So by that, this function could take actually different forms, but if we think about it, typically when we're doing like on policy prediction, we think of it as trying to find v pi of s. So we're trying to find the value of s under the policy pi. This is what we've been doing until now. But now, instead of trying to find the value of v pi of s, we're trying to find the value of this v of s, comma, some vector w. Right, so this is actually I'm trying to make it bold, but yeah, that's actually what do you call this? It can be a vector, it can be a matrix, depending on how you're viewing it. But the whole point of using this function approximator, which once again, this could be a linear function, it could be a neural network, it could be a decision tree. The point is that our state is now parameterized by some function w. So that means that when w actually changes, it won't just change for the value of one state, it might actually change for multiple states. Because when we update a particular state, we actually affect the value of other states. Sorry, because this is assuming that for us to actually be doing this, we would be assuming that W, the dimensionality of W, should be like much smaller than the number of states we have. Because that's the only reason why we would actually try to use a function to approximate the value of a state. So this solves certain problems and introduces other ones that we'll actually go into in this video. So now that we know that what we are trying to estimate is this, just to give you a picture of what that looks like, for instance, here we've got all the states, but W could be just like a vector of, let's say, 3 dimensions or something of the sort. So it could just be W1, W2, or W3. And actually, I think it's better if I give an example later on to make things much easier. So let's actually start from thinking about like your typical supervised learning problem. So for instance, in the case of Monte Carlo, we've been thinking about this as we have a particular state st, and our target when we're trying to find v pi of st is actually gt. This has been our target, right? When we're thinking about Monte Carlo rule, and when we're thinking, for instance, about td0, we would be saying like, okay, our target in this case would be rt plus 1 plus gamma v of st plus 1, and this is obviously going to be parameterized by w t. So I'm just writing wt like this, but please just assume it's a vector in this case. So when we are actually thinking about the Monte Carlo, or we're thinking about the TD, when we defined what is the Monte Carlo target and what is the Monte Carlo, the TD target, this is how we define them. And so we need to make sure that the algorithm that we are actually using I should say the way that we're actually trying to represent this, whether it's by a linear function or neural network, we need to think about how it should be also able to chase what we call non-stationary targets, because these values will actually continue to change the more we learn. And again, I will make it clear what I mean by this. But like I mentioned, typically we would have more states than weights, and we should therefore decide which states we actually care about, right? And to decide that, we use a different function that we denote as µs, right? And this should be greater than or equal to 0. And we say the summation over s of mu of s should be equal to 1. So what is this µs? Once again, let me write this down to make it clear. This represents how much we care about the error in each state S. Because since W is much smaller than S, that means the error in some states might be higher than other states. Like for instance, if we completely reduce the error in one state to 0, that could come at the expense of having a higher error in a different state, because you can think of W as something that is limiting the resolution of in how we represent our state space. So for this, first of all, when we say it represents how much we care about the error in each state S, we actually need to define what this error is. So we define what we call the mean squared value error, right? And this mean squared value error is the objective we try to minimize when we're actually trying to learn the true value of a given state. So please do not forget the objective here is we want to we're trying to find the true value of a state that we represent by v pi s, but because the state space is large, we represent this using this function approximator that is parameterized by w. And then we have mu s over here that represents how much we care about the error in each state. The error itself is defined as, we say, VE, right, of W, and we define this as being equal to the summation over all states of mu s, which again is representing how much we care about the state. And here we have v pi of s minus v of s comma w squared, right? So this is the approximate value of s, right? This is the approximate value, and this is the true value of s. So one thing that you might end up asking yourself in this issue, like, I mean, it's a perfectly legitimate question, is we don't actually know what the true value of s is, right? So why do we have this function in here where we are subtracting? I mean, we can get the approximate value of s given some representation of w, but in this optimization objective, or in this error term, we actually we're giving this true value of v pi of s, but we don't know what this is. And this is true. And we're actually going to go through how we can modify this function to more accurately represent the actual things we're trying to learn and the actual things we actually have available. But as of now, just assume there is some I don't know, some oracle or something that just gives us like this true value that just tells us that, well, v pi of s is given, now try to learn. So for now, just assume we have this, but later we're going to remove that assumption. So another thing to note about this value mu of s is that usually it is, well, the way that we choose it could be as a fraction of the amount of time we've actually spent in the state S. So we call this the on-policy distribution. So that's what we call this mu of S. And again, our goal then becomes to find, let me write it in a different color to find VEW of W star that is less than or equal to VE of W for all values of W, right? This is what we're trying to find. We're trying to find a set of weights that actually minimize this error that we've got here. And to do that, we are going to focus on certain methods certain, should I say, gradient methods. So let me set a new page to discuss this. So we're going to be looking at stochastic gradient and semi-gradient methods. So if you are familiar with supervised learning, you might already know what stochastic gradient descent is, and maybe the semi-gradient methods may be new to you, but we're going to be discussing this. So we're going to be talking about stochastic gradient and semi-gradient methods. Right. So stochastic gradients and semi-gradient methods. So this is, to be more specific, we call this stochastic gradient descent, which is what we're going to be showing here, which is usually denoted as SGD in the machine learning community. So let's actually talk about the things we have. We have our W, which again, let's assume this is a vector, and therefore it should take the scalar values W1, W2, all the way up to WD. Right, that's our W. And we have this V of S comma W, which is what we're trying to learn. And we have this, we assume that this is differentiable, by the way. This should be differentiable. And the final thing is we're gonna have our normal time steps, like t going from 0, 1, 2, up to whatever value that we might end up, which can be n or whatever, or it can be capital T, but it doesn't matter. And we'll be updating W in each time step, right? So to better represent, we're gonna represent W as W at time step T. So please don't confuse this as like this means W1, W2 in terms of the actual scalar products, but this is the entire vector here at time step T, right? So this subscript is denoting the time step, not the actual W element. So for now, let's assume we're given some state st and its true value under some policy pi, which we'll denote by v pi of st. So as I assumed before here, we're assuming that we know the true value of this, right? So we're going to assume, let me write it here, maybe in a different color. So we're going to assume we know v pi of st, right? So we assume this is given to us. And the problem is that not w that like we don't have a value of w that will get like all the value of the state to be correct, their true value. Because of this limited resolution problem I talked about, where w, the number of elements in w are much less than the number of elements we have in our state space, which means that w first of all has to prioritize which states are important. Well, not w, but probably the mu value we have. But not only that, we need to minimize the errors across all the states, right? So we assume we know, so this is our first assumption. And another assumption we'll make is that we'll assume this mu is uniform across all the states, right? So that we don't actually deal with, right now we don't want to deal with which states are going to be more important, since we're just going to make this more general. So what stochastic gradient descent does, right? It tries to like adjust the weights. It tries to adjust W, right? By like a small amount. In the direction that would minimize, or should I say reduce, the error. Right, so let's give an example of a single sample and how we'd go about minimizing it. So we say that if we want to find the next value of w, say wt plus 1 at the next time step, we're gonna start with whatever value of w we started with. This can be arbitrary or it can be random, or like, yeah, pretty much. And we subtract 1 over 2. This is just needed for, well, you'll see why in a moment. But the gradient of v pi of st, which again we assume we're given. Let me write it in a different color so that we can, v pi of st, we assume that this is given to us, right? Minus v of st comma wt squared, right? So if you remember, we had defined this as the, like, well, the mean squared error or and stuff, but to actually reduce the error, right, to minimize the error, we need to take the derivative of it, in this case, or the gradient, I should say. It would be a more accurate description. And if we actually compute this, what we'll end up with is this is equal to wt plus alpha. So now you see that the 2 was there just to help us cancel this, but since it's a constant, it doesn't actually matter, by once more, I should write this in a different color, v pi of st. So we're taking the well, we're just using the chain rule here, v pi st minus v of st comma wt times the derivative of what's inside, which is the gradient, right? This is with respect to w, which is why we only differentiate this part, of st comma wt, right? So if we denote this as, this is a, representing a, and this is b, denoting it as this because we will need to reference this later on. So this is, well, essentially the objective function that we're trying to minimize. So we take the derivative with respect to w. And if you're, if you're familiar with machine learning literature, this should not be new to you. So we consider alpha to be our learning rate, right? We're going to take a small step in alpha, and we're going to consider this of a given function to be essentially the partial derivatives with respect to w, right, of w1, partial derivative with respect to of the function w with respect to w2, and so on, and the partial derivative with respect to w to the d. So this is essentially what this term actually means, like just taking the partial derivatives here. And so since we are moving in the direction that's proportional to the negative gradient, that's why this entire process is called gradient descent, right? So essentially one question you might have at this point is, why are we taking a small step? Like, could we not just take the entire step? Because here we're saying what this alpha usually is a very small value, so that we just take a small step from our true value of w, right? So if we take an entire step, we can eliminate the error completely in this particular state. But what we need to remember is, since this is an example for one particular state, we are trying to minimize the error across all the states, right? So not just a single state. So to balance the errors in the different states, we want to minimize the total error. That's why we take only a small step, because imagine taking a large step, like if we didn't have a small alpha here and we were just minimizing the errors as is, That will mean fine, the error might end up being zero in this particular state, but it will come at the expense of like the error being much larger in a different state because of the limited resolution problem that I was referring to before. So in order to avoid that, it would be advisable for us to actually um, like take a small step error, right? Okay, so we've moved one step further. So what we know is if someone gives us the true value of v pi, we have a method that we can use to minimize the error, find the optimal value of w, and in turn find the value of a particular state parameterized by some value w. Because if we really think about it, all we need is to find w and we'll know the value of the state, at least under these constraints. But now we need to remove this assumption, right? So let me insert a new page for this. We need to remove this assumption that we know v pi of st, right? So if we remove that assumption, as it could be in an ideal case, because we could have a bootstrapping target, like in the case of TD learning, and like it would actually take multiple iterations before we know what its actual true value is. But what we have essentially, like, okay, instead of this miraculous v pi of st that we assume that we're given, what we'll truly have in any algorithm that we end up deciphering is a more noise corrupted version of v pi of st, right? And this would have like so I should say noise corrupted would have, right, instead of this would actually have this, right? This is what we'll actually have in a typical scenario. And like we can actually represent this by let me use this noise corrupted version. Let's just represent this as ut, right? And this, you can think of this as, well, it could be whether the Monte Carlo target, it could be the TD target, and it's not this. We don't actually know what the true value is, at least in the beginning. So essentially what we are trying to find is, once more, I should say, wt plus 1 is equals to wt plus alpha times, instead of v pi of st, we have ut, which might be better represented with a different color here. We have ut, minus v of st, comma wt, times delta v of st, comma wt, right? Just make sure that this is, yeah, the same as what we have there. So we have the situation, so we have this ut now, which is a noise corrupted version of this. So what kind of values could ut take, right? And is it really okay for us to replace v pi st, which is the true value under some policy, with this conspicuous ut that we're given here? Well, if ut is an unbiased estimate, right, which means if the expected value of ut given st is equals to s is equal to v pi of st for all values of t, right, then there are guarantees that w will definitely converge to some at the very least some local optima. Like it can be a local minima, it can be a global minima, depending on the kind of optimization objective we have. but they are this we can actually we can actually make guarantees of these convergent properties if ut is an unbiased estimate, right? So if we think, for example, the Monte Carlo target, right? The Monte Carlo target is GT, right? So if you think about Monte Carlo, we start in a state, and what we're actually trying to find when we are doing Monte Carlo is the expected value, right, of GT in a particular state. So we call like the expected value of GT given, some value ST, and this eventually gives us V pi of ST, right? In the case of Monte Carlo, we've seen that this is the case, right? So we can say that the update rule for Monte Carlo would be unbiased. Therefore, we can actually write this as for Monte Carlo target, we can write this as W is actually equal to W plus alpha times GT, right, minus V of S comma W times the gradient with respect to V of S comma W. And the reason why we can do this in terms of Monte Carlo here is because the expected value of GT is V pi of ST, and therefore GT is an unbiased estimate. Therefore, like, we can make this, and W is definitely guaranteed to converge, right? So that means in case of Monte Carlo, this is okay. We don't actually need to have the very true value of this. We can just use the Monte Carlo target from a particular state, and it should be okay. But when we're thinking about bootstrapping methods, for example, if we think about the TD0 target, then things are a little bit different. So we know that when we're talking about TD0, what we have is something of the following sort. Oh, maybe this is not clear enough. So when we're talking about TD0, we know that we are dealing with R plus gamma times V of S comma W. So already you see the problem here, because the target itself, because in TD this is our target, and the target is actually depending on the current value of W, right? So when we think about TD methods, actually the way we would represent this is by saying, well, okay, therefore, just to make this consistent, TD target, if we're using our method, we say that W takes the value W plus alpha times R plus gamma V of S comma W minus V of S comma W times, this is how our update rule would look like, right? And this is our TD target. Now this is definitely biased, right? Because if we go back, right, like we can ask ourselves, if we go back here, like, how can we move from A to B without assuming that the target is independent of W, right? Because when we look at how we moved here from A to B, when we're computing this derivative, so when we're computing the derivative of what's inside, we only computed the derivative for this term, right? That's the gradient that we have here. And the reason why we did not compute the derivative for this term is because this does not depend on W, right? So this does not depend on W in this particular case, which is why we didn't compute the derivative of it. But now, so in the case of Monte Carlo, this isn't a problem because we've got GT, and GT also does not depend on W. But this target here actually depends on W, which means when we're actually making this derivative, instead of just taking this the derivative of this the expected value here, or I should say the not the expected value, but the estimate, we take the derivative of the estimate, right? But we don't take the derivative of the target, right? Because we're using the same form that were given here over there, but the derivative of this is the derivative of the estimate, but the derivative of the target is not actually shown. So there's already a bias, right? We include the gradient for the target, but not the gradient for we include the gradient for the estimate, but we don't include the gradient for the target. What this means is that part of the gradients are left out, and this is why these methods are called semi-gradient methods, because they only include part of the gradient. They don't include the gradient of the target variable. So automatically, if you're quite observant, you already see a problem with this way of writing our target, because if W is, for instance, some neural network or some linear function or whatever it is, you might think, okay, if the target depends on W and the estimate depends on W, like it seems like we're chasing, once again, a non-stationary target. But how are we going to control these W variables to ensure that learning can be done properly? So specifically, let's talk about neural networks. Like there are different ways that we can use to make sure that we can still learn, like when we have this two different kinds of W's. When we have the same W's here, both in the target and in the in the estimate. So one way we can think about it is at certain time steps we can freeze the weights, and then we'll have two different versions of W during a certain point in time. So there are like different ways that we can use to make these updates, but I'm not going to cover them in this particular lecture. I'll cover them probably in the upcoming lectures, because we're going to start talking about more specific examples as to how we can actually use these networks or how we can actually use these function approximators to help us solve more complicated reinforcement learning problems. So probably in the next lecture, when we start talking about on policy for the control problem with function approximators, we might actually go through an actual example, the coding example, and see how it is that we can translate all these notations that we've denoted here into practice. So I hope from this lecture you got a basic overview as to why it is necessary for us to use function approximators when we are dealing with large state spaces, and why these approximators actually help us in simplifying problems, what kind of advantages they have, and what other problems they could lead to, and how we alleviate such problems. So since this is only an introduction, but in the next lecture we're going to go into more detail as we go into the more practical solutions for this. So I'll end the lecture here. Thank you for your time.